Hello, this is Jake Abbott. In previous videos, we've learned that using state feedback, we can effectively make our system eigenvalues be anything we want, which means we can control our system's stability and time response properties. And we've learned how we should, what value we should set the input at such that the output goes to some desired output. We called that the tracking problem. We do that with state feedback. What we're going to talk about in this video is making that tracking robust and being able to reject disturbances that our system might have. So in the prior video, this would have been the video on tracking, we learned that basically we can find the DC gain of our system. If we know our system is stable, then we can find the DC gain of our system, and we called that thing some GDC. And we learned that if we set some R value as our input, then the output Y in the steady state will be equal to our R times our DC gain of our system. And we said, okay, if that's the case, then why don't we let R equal our desired output Y over our DC gain, and if we do that, then our steady state Y will equal our desired Y, and we'll get this result that we want. The problem with this is this, what we have right here is our actual system DC input, our DC gain. What we have right here, what we're implementing in R, this is actual. What we have in our sort of controller input is our estimate of our DC gain. And this is based on a model of our system. We're going to take our R, we're going to make R be equal to our desired Y, which is the thing we want, and we're going to divide it by what we believe our system's DC gain is. The problem is we don't know the actual DC gain. We know an estimate of the DC gain. And so basically the actual Y will go to some value that will be off from the desired Y by whatever modeling inaccuracies we have. If our model has a 10% inaccuracy, then our output will have a 10% inaccuracy. So this is a problem that we didn't really deal with in the tracking problem originally, and now we realize, oh, okay, so modeling errors are going to have an effect on our output. So that's one reason why we want to make our system more robust. We would like our system to somehow, our control system, to work even if our model has problems. And the basic logic of this is, if we can see our output Y, and we can see it's not quite going to the desired value, there should be a way to take that information, the fact that we can see it's not perfect yet, and push our system in the right direction. So that's what we're going to do here. This is for modeling inaccuracies, but it applies to disturbances and things that are external things, not problems with the model, but actual disturbances that aren't part of our system model. So imagine we have our original system that we've been playing with that looks like x dot equals ax plus bu, and x is our set of system states, and u is our set of system inputs. Now, ideally, we would have complete control of our system inputs. These would be, forces and torques from motors, and they would be voltages coming out of our computer. But in reality, there are other things pushing on our system than just our inputs that are these perfect inputs. So in reality, this is really some u plus w, where u is our actual inputs that we have control over, and w is this set of disturbances that can come in like inputs. So imagine this is a wind gust. If our control input is a force that's pushing on a mass, then other forces like a wind gust act as disturbances on that system. If our input is a voltage, let's say, coming out of a D to A card, well, if you command 5 volts to your D to A card and it actually gives 5.1 volts because it has a bias, that will come like a disturbance here. So we in general can have disturbances that can come into all of our inputs, and we'll call those disturbances W. And so if we're going to think of systems like this, then we need to be more realistic about what kinds of inputs we have, what kind of modeling inaccuracies we have. And in this lecture today, we're going to find that by modifying our system controller, still using state feedback but doing a modification to it, we can solve both of these problems. We can make a system that's robust to modeling inaccuracies and robust to external disturbances. So that's the topic of today's lecture. So I'd like to draw out a diagram, a system diagram of this system that we have here. And then of course we have our y equals c times x that we'll have to add. So let's do that. So I'm going to give myself a lot of room. So let's say here's our plant. And I'm going to hide as much of the A, B, and C from you as I can for a while. And let's think of what the input to our system is. So we have this system that has input, and I'm going to call this input U bar, because in reality we just found that our input really consists of two inputs. There's the input U, which is this thing that we have control over, and it's added to this W, which is our disturbances. So this U bar is what we'll call our total plant's input, which is the desired input and disturbance inputs. And out of our plant comes our state vector, and I'll use this double vector to show that it's not a 1 by 1 thing, it's an n by 1 thing. And that goes into our C matrix, and then out from our C matrix comes Y. And then we've said in the previous videos that we're going to implement state feedback. So I'm going to have this gain K, this gain matrix K, and I'm going to multiply X times K, and then I'm going to take that thing and I'm going to sum that up here with some other signal V. Now this would have been the signal that in previous videos we called R, but we're going to do a modification now. Now I want to make a quick note here. In previous videos and lectures we'd been talking about doing something like this, where we say we're going to make U equal R minus K times X. Now this minus sign, that's an arbitrary choice. If I would have put a plus here, all it would have done is given me negative signs in the K. So that's a sort of an arbitrary choice if you want to call it a minus K or plus K. And we called it minus K. Well, at this point, the Chen book switches notation and starts using a plus K, so I'm just going to switch notation with the book to stay consistent. But let's be clear, that plus or minus has no bearing, since these K's are completely floating constants that can absorb that plus or minus sign. Okay. Now that's a little bit of a distraction, so back to our main point. So now we have our V here, which is going to be some desired signal that we have, and the question is, how are we going to choose that V? So what we're going to do is we're going to take our reference. Now this is, remember, R is effectively what we're going to set our Y desired to. That's what we'd like to do. And we're going to take that and we are going to sum it with minus Y. So let's draw arrow straight back like this. So this signal here that's coming out is R minus Y. So effectively, if we let ourselves think of R as Y desired, this isn't what we did in the past tracking. In the past tracking, we weren't doing a robust method, so we were setting R equal to Y desired over the DC gain. That's not what we're going to do here. Now we're going to think of R itself as our Y desired. So now this thing here coming out of here is an error. And if Y is exactly equal to R, then we have no error and we'll be able to use that information. And so now we're starting to think about our controller in a more kind of classical way that looks more familiar to people who've had some classical controls. So we have a desired input signal, an actual output signal, and we're going to let the error between those guide our system. So now what we're going to do is we're going to implement an integral controller. So what we're going to do is we're going to pass this through. I'm going to put a 1 over S because it's a sort of an abusive notation because everything else is in time domain, and I'm going to write a little Laplace domain 1 over S, but it means the integral with respect to time. I'll put integral dt underneath it. So I'm going to integrate the error, and out of that integral, I'm going to get a new signal that I'm going to call x sub a. And so this is we have our original state vector x, which is an n by 1 thing. And I now have this augmented state that's going to come out. And that's a 1 by 1 thing. So this is a scalar because R is a scalar and Y is a scalar in this conversation. So I've added a new augmented state, and I'm going to pass that augmented state through a gain. I just want to give myself the option. So let's call this an augmented gain, K sub A. And that's what I'm going to let my signal be. And because my error is being integrated into a signal that I'm going to call x sub A, I can also think of this error as being xa dot, just because the definition, if I take the integral of xa dot, I'll get xa. So now what I've done is I've made a system that basically finds the error between my desired signal and my actual signal. It integrates that error over time, multiplies it by some gain, and we don't know yet what that gain might be, but we can think of it as a 1 for now if we want. So we have this signal that's encoding not only our system's error, but has our error been wrong for a long time? Because if even a small error over time, its integral will become big. And then it's that signal that we're going to give to our system. So the logic of this is fairly straightforward. In the event that there is no error between our desired signal and our actual, then the integral of 0 gives a 0, and we basically tell our system, don't do anything. You must be doing everything right because your signals are tracking perfectly, and don't do anything. When we have an error, either a big error for a small period of time or a small error over a long period of time, that has the effect of pushing our system in a direction that will get rid of those errors. The great thing about this is that error is going to be there, whether it's due from plant modeling inaccuracies or this W disturbance. So we're going to be able to reject either of them, and the rest of this lecture is to show that that truly is the case. So I'm going to summarize in some equations what we've drawn in this diagram here. So we have that U, which is our actual controller input, is rather than being R plus KX, which is what we did in the last lecture, now we have U equal, so I want to make, this is not what we're doing. Rather than doing that, we're going to have some Ka times the time integral from 0 to whatever time we're currently at. We're going to be integrating R minus Y d tau from 0 to time, and then we're going to be adding that to Kx. So we still have this state feedback term here, but that's just part of it. It turns out now that this state feedback term is still going to be used to set the system eigenvalues just like it was before, but now we have this new variable. And we also have this other equation that we have xa dot is going to equal R minus Y, but Y is equal to C times X. Oh, sorry, that's a minus sign. C times X. And if you actually go through and do all of this algebra, what you'll get that U is equal to our original K, and remember this is a 1 by n thing, and then we've augmented our K with this new K sub A, and this is a 1 by 1 thing. So we have this new K matrix, and then we have this new state vector, which looks like X and X sub A. And this is an n by 1 thing, and this is a 1 by 1 thing. Oh, sorry, 1 by 1 thing. So now we have this big, basically it's a 1 by n plus 1 matrix, and an n plus, an n plus 1 by 1 vector. So we've just added one state to our existing state vector, and we've added one gain to our existing gain matrix. So we've grown our system by 1. And if we do that, we can finally pack our system into something that looks like this. We have our original X dotted, and we have our XA dotted, and that's going to equal A plus BK, and if we would have had our minus K, that would be A minus BK. So this is basically our original state feedback matrix that we've seen for a couple of times now. We have a minus C here, we have B times KA, and we have a 0. So that's our new, effectively our A matrix. Here's our augmented state vector. And then we have 0, 1 times R, and we have a B0 times W. And then our Y is equal to our old C matrix times 0. We have X, and we have X sub A. So this is our new A matrix, and it's an n plus 1 by n plus 1 matrix. So we've just grown it by 1. And we have R and W coming through different effective B matrices into this new matrix. Okay, so the one thing we know from before, that if the pair AB is controllable, then we can use this K matrix to set those system eigenvalues to be whatever they want. There's a proof in the text that I'm not going to go through that basically says if the pair AB, the original AB from our original system, if that pair is controllable, then this new matrix, this new augmented K matrix that is one gain more, can be used to set the eigenvalues of this new A matrix to any value that we want. So this idea of controllability is maintained, and we can make this have any eigenvalues we want. And so what we're going to do is we're going to make it have nice, stable eigenvalues with good time responses that we want. Okay, so to now talk about how this is going to help us, what I want to do is I'm going to zoom in on this part of the plant here, where we're passing we have our V, we have our U, and we have our W, and we have our U bar, and we're looking at all of these different signals that go into our plant. So now I'm going to erase this whiteboard here, and I'm going to start with a zoomed in version of this part of the plant. So what I'm going to do is I'm going to redraw. So here's what it looked like before. We had V. That was going into a summation junction with K times X, like this. So this was KX. And then what came out of there we called U, and then that went into a summation junction with W, and what came out of there is U bar, and that's the actual, what our actual system perceived. U is the thing we had control over, W is the thing we didn't have control over, so our real system was getting pushed around with U bar. So what we're going to do is we're going to take this thing and realize that we can transform this like this. So I'm going to have V come into a summation junction with W, like this. And what comes out, I'll call that thing V bar. And then I'm going to take that signal and pass it into a summation junction, like this, where here is K times X. And what comes out is U bar. Okay, now the one thing that I want to make really clear is we didn't change the U bar. U bar is still the same equation. It's still K, if you look at the original, it's K times X plus V plus W. And that is maintained here. It's K times X plus V plus W. So U bar didn't change, so we haven't changed our system. So now what we're going to do is we're going to say if we can rewrite things in this way, it lends to a little bit easier way to analyze our system. Okay, so now what I want is I want a transfer function from V bar to Y. Okay, so I'm going to cut my system right here and try and get this transfer function. So transfer function from V bar to Y. And so let's define this thing as G bar, okay? And so if we actually go through and do this, what we're going to get is we're going to get that G, and there's just some algebra here that we don't want to show every single step, but it's going to equal C times SI minus A minus BK inverse times B. And if we notice what this is the transfer function of our original state feedback system before we did any of this augmentation business. Just when we originally fed back the states through the gain matrix K, A plus BK was our new with state feedback A matrix that we could set the eigenvalues of. So this transfer function describes that system before we did this integration external loop. Okay, so this G bar transfer function, we can always think of that as a numerator over a denominator. So let's call the numerator N bar and then the denominator D bar. So let's just remember right now, this is going to keep coming up for the rest of this lecture, that whenever we're talking about the bar system, this is the original state feedback transfer function that we can make its eigenvalues be whatever we want them to be, but before we closed the loop and added the one extra augmented state. We can also draw this system as a loop diagram. So let's do that here. So let's think of this box here as our G bar system. And so out of G bar comes Y, and into G bar comes V bar. And then if we go back up to our original drawing, we say, okay, well, what is V bar? V bar is equal to V plus W. And what is V? If we go back to our diagram from the previous slide, well, V is equal to, it was equal to Ka over S, and I've just combined the integrator and the integrator gain into one block now. And what went into the integrator? Well, that was the error. That was the difference between R and Y. So nothing has changed here. We've just regrouped things a little bit differently, but this is the exact same system from before. But it just lends itself to being analyzed a little bit easier. Okay, so we already know that the denominator D is the characteristic equation of this original transfer function. And so I'm going to just call that, characteristic equation sub S of our original system. Okay. So what we're going to do now is we made this big augmented system that's this n+1 by n+1 system, and that new system had that bigger A matrix, and if we take the determinant of that matrix, so I'm just going to rewrite what that A matrix looked like. We had Si minus A minus BK, and then it was a minus C, so that becomes a C, and then there's a BKA, so that becomes a minus BKA, and then there was a 0, so that becomes an S. So if I take the determinant of Si minus that big A matrix, that's this new characteristic equation. So let's call it characteristic equation sub F, meaning the with the extra feedback loop. So this is the characteristic equation of our new augmented system, and this is an n+1 order polynomial. And we know because of controllability that we can make its eigenvalues be whatever we want them to be through our, that should be a K, through our K matrix, which consists of our original K plus this new augmented K. We can set these poles to be whatever we want them to be. And so we're going to set them equal to some, S minus lambda 1 times S minus lambda 2, ... So we have complete control over these poles and these eigenvalues. So there's one thing I want to show you really quickly, something that's really easy to verify. And some smart person found this out at some point. If I take this matrix, identity, and you can check this for yourself afterward if you'd like. And if I take this minus C times Si minus A minus BK inverse 0, 1. If I take this matrix and I multiply that by, now I'm just rewriting this matrix here. So Si minus A minus BK, I have a C here, I have a minus BKA, and I have an S here. If I take these and I multiply them by each other, what I will get is a matrix that looks like Si minus A minus BK, a 0. Here I'll get S plus C Si minus A minus BK inverse BKA, and then I get a minus BKA here. So basically, if I take these two matrices and multiply them by each other, I get this matrix, and the reason why I would want to do that is because I have this 0 here. So if I wanted to find the determinant of this new matrix, that's just equal to this times this minus this times this, but because of that 0, that's not going to matter. So I can actually see the determinant of this now by inspection. I just have to multiply these two diagonals. So let's go back, and I want to name this first matrix matrix 1, M1, this matrix here M2, and let's call this matrix here M3. And so we have this equation that M1 times M2 is going to equal M3. Okay, now There's another trick from linear algebra that says if I take the determinant of M3, that's going to equal determinant of M1 times determinant of M2. So this holds for any matrices that you multiply together. If I multiply matrices together, their determinants multiply to become the determinant of the new matrix. So if we start looking at these matrices, you realize that the determinant of M1, because of this 0 here, it's just the product of the diagonals. So it's an identity times a 1, so that's just 1. So I have determinant of M1 is equal to 1. And when you start looking at M3, you say, excuse me, I want to look at M2. If you start looking at M2, that's this matrix we already found the determinant of, and we've called that the characteristic polynomial of our new desired system. So the determinant of M2 is going to equal our closed loop feedback characteristic polynomial that we have control over. And then if I look at this new matrix, this M3 matrix, we already talked about it being block diagonal. Let's call this entry, since this is this whole matrix is M3, let's call this matrix M3(1), and let's call this matrix M3(2). And let's realize what the dimensions are here. M3(1) is an n by n matrix, and M3(2) is a 1 by 1 matrix. It's just a scalar. And so when we do that, we can say, okay, well, so what is the determinant of M3? Well, that's just equal to the determinant of M3(1) times the determinant of M3(2). And so, and I can actually physically see what those matrices are going to look like. And M3(2) is a scalar. And then the last thing, oh yeah, and then M3(1), so this is a scalar. Determinant of M3(2) is M3(2). So this thing just is M3(2). The determinant of a scalar is itself. And then what is the determinant of M3(1)? If I look at M3(1), that's just my original system. So this is my original characteristic equation. But we already said that that's also the denominator, d bar, of our original transfer function. So I know what this term is, and I know what this term is. And then now you just put everything together. So I'm going to put these things on one side of the equation and these things on the other side of the equation. And so I'm going to get that 1 times my closed loop characteristic polynomial is going to equal my determinant d sub s, or d bar of s, times s plus g bar of s times Ka. And then I'm going to realize that 1 times anything is itself, so I'm going to get my closed loop characteristic equation is equal to, and I'm going to do a little factoring here, and I'm going to say this is equal to s times d bar of s plus d bar of s times what g is, which is n bar of s over d bar of s times Ka. And then I'm going to notice the simplifications that come out by canceling things out, and I'm going to have s d bar of s plus Ka, which is a scalar, so I can move it to the other side, times n bar of s. So this is my relationship for my new closed loop characteristic equation. It equals s times the characteristic equation of my old system plus Ka times the numerator of my old system. That's what this closing this robust feedback loop did for me. It isn't obvious why that is good at this point, but that's what it did for me. So now what I want to do is I want to calculate the transfer function from my disturbance w to y. Okay, so what do we want to have happen here? If I have my input w come in, which is a disturbance, what do I want that to do to y? Ideally, I'd like it to do nothing. So in the steady state, I would like a system that this transfer function has a DC gain of 0. I want w to come through and get multiplied by a 0, so I don't see it in the output. I don't want to see the disturbances in my system output. So I'm going to make this transfer function. Let's call it GYW of S. And that's going to equal the ratio of the output Y to the input W if I write them in Laplace domain. So I'm going to write this actually out. Y of S is going to equal to G bar of S times, and this is going back to our original, or our second system diagram that was a couple of slides ago. It's going to equal W of S plus Ka over S times Y of S. So go back to the system diagram and you'll see this just is completely evident from that diagram. And so if I expand that out, I get G bar of S W of S minus Ka times G bar of S over S Y of S. And then I can group the terms, so I can pull this term which has a Y over to the other side with that Y, group those terms and pull them over. And if I do this, if I do all of this algebra, what I can eventually get to is I can get to that I have my transfer function from W to Y of S is written like this. So in the denominator I see S times D bar of S plus Ka times N bar of S. And in the numerator I will get an S numerator of S. So this is my transfer function from W to Y. And if I look at this, I can say I already called this thing my new closed loop characteristic equation, delta sub F, and that's underneath S times numerator bar of S. Okay, so let's remember now that we have complete control of, because of controllability, of our system eigenvalues, and we're going to choose those system eigenvalues to be stable. So we know that the roots of this characteristic equation, so the roots of the denominator of this transfer function, we know we don't have any roots at 0 because we made it that way. We made our roots all stable, meaning they have negative left-hand plane parts. So we know there are no roots at 0. So if we calculate the DC gain of this transfer function, which the way we calculate the DC gain, if you remember from your signals classes, to find the DC gain of a transfer function, I just evaluate it at S equals 0. And just as a side note, this comes from the final value theorem. There's a relationship that goes between time domain and S domain, where if you want to find what your signal does as time goes to infinity, you effectively start looking at what your Laplace domain signal does at S equals 0. And so that's where this DC gain originally came from. So we're going to analyze our system at S equals 0, and if we do that and we go up here, we know that the denominator, as S goes to 0, it goes to some finite number. We know it doesn't go to 0 because we know we don't have any poles at 0 because we place them to be all stable. But we do have this S in the numerator, so no matter what N bar is, it completely doesn't matter because it's something and we're multiplying it by 0. So the numerator goes to 0. So we have 0 over some non-zero number. So the DC gain of this transfer function equals 0. So we've just proven that in the steady state, if we have some disturbance W, as time goes to infinity, that effect of W on Y will go away as time goes to infinity. And the great thing about it is it doesn't matter what D bar or N bar are. This holds true regardless of what they are. So this statement is true even if our system model is incorrect. It doesn't matter what they are, they just all cancel out. So basically we've just created a controller that even with modeling errors, we can prove that a steady state disturbance will be completely rejected by our control system. Now, that being said, we say that it doesn't matter what our model is, but we did make this assumption that our system was stable. And so if our model is so bad that even though we think we've placed our eigenvalues to be stable, if our model is so bad that is violated, then this will break down. So there is that caveat that we're robust to modeling errors provided our modeling errors are not so bad that it fundamentally affects our stability assumption. So, similar techniques to what we've just developed above can be used to calculate a transfer function that maps how y relates to our step r. And if we were to do that and call that transfer function gyr of s, what we would get is a transfer function that looks like the same denominator, the same characteristic equation of our system, and then in the numerator we'd have a ka n bar of s, and if I expand that thing back out, I'll have ka n bar of s, and that denominator looks like s d bar of s plus ka n bar of s. And then we know that this delta f is our characteristic equation of our augmented matrix, which we have full control over. D bar was the characteristic equation of our original state feedback matrix before we did the augmentation, but we have complete control over those eigenvalues as well. So we know that D bar doesn't have any roots at 0. And so if we do the DC gain of this system, so we say let's look at dy of r of s evaluated at s equals 0, what you'll see is that we know there are no zeros here, but there is a 0 here, and this whole thing goes away, and we just basically get ka times n bar over ka times n bar, and that thing by definition equals a 1. So we now know not only the previous result was if we have a step input in disturbance, it will be rejected over time to 0, and if we have a step input in R, it will pass exactly through into Y, and this doesn't presume that n bar is accurate, so our model doesn't have to be accurate, because even if our n bar is inaccurate, we're dividing it by the same n bar. And so we have this system that has a perfect DC gain of 1 for our desired signals R, and it has a perfect DC gain of 0 for our disturbances. And the same assumption here holds that this is all true provided that our model isn't so bad that our stability result is violated.